Hoş geldiniz.
Hello everyone, distinguished guests and colleagues. Now we are opening our new session, which is on construction process and management for wind power plants in Turkey. And we are going to give some details to you all. I am an electrical engineer, and I have been working on these subjects for many years, which is a very exciting subject, because in the first place, wind turbines set up and their costs and their project investment, it's a very interesting subject. And wind power plants operated for almost 30 years. The details regarding to this matter is very important. For this reason, our speakers are experts also in their fields, and they're going to give details. As you know, we haven't been through a very easy processes. When I started as an engineer, we have been through very tough times in the sector, both bureaucratically and for both workers. And wind turbines were not a system, so for the formation of this mechanism, you should be very experienced. But still, in 1980, since 1980s, 3.5 or 4 gigawatt, it paves the way for us. So it's very important. And for this subject, firstly, our speaker is Mr. Ziya Genç from Siemens, and he is going to inform us about his works, and we are going to, it's going to be very useful for us.
Hoş geldiniz değerli katılımcılar.
Welcome to the session, ladies and gentlemen. As Halil said, I am working as a service sales manager for Siemens. And for the last 2 years, I've been dealing with the product sales of wind. I think that one of the most important components of the wind power plants is remote control and remote diagnostic services. I will give you some figures and we'll try to elaborate on the advantages of providing remote diagnostic services. When it comes to service, particularly for the wind power plants, the main purpose is, of course, to minimize downtime and to optimize generation and to bring it up to the maximum level possible. So when doing this, it's not like the gas turbines, steam turbines, or these are not confined spaces where you just put some input or fuel, otherwise wouldn't put. To put it simply, you don't have the chance of switching on and off for those components. And as you would know, we start with a height of 80 meters, where there is the possibility of turbulence. In offshore turbines, corrosion is a major problem. Therefore, it's like a small kid that needs to be monitored all the time. Doing it through the human hand is not very effective. Therefore, when the wind industry, particularly for maintenance, I think we're heading to digitalization and remote monitoring. I think that the presentation will cover all these aspects, and let's hope if the presentation will give you the take-home messages. Now, the slide very simply provides an introduction to RDS, Remote Diagnostic Services. And there are four main pillars, one being the remote monitoring, 724 providing remote controller monitoring. The other one is diagnostic support that would just involve the site team, local team, plus the investors also would just need to be advised by this unit. Software updates are quite important because the system is a learning system. It's a continuously evolving system. Therefore, we make this sure with the diagnostic support and the software updates. The fourth pillar is the vibration diagnostic, which also makes it possible to have an early detection of the potential breakdowns. We consider this as an essential element of our service packages. On the left side, it's 100B. It's just scheduled service. It's a simple program. But other than that, in all of our service programs, remote diagnostics are always included. And as I said, the four components, vibration diagnostics, diagnostic support, and round-the-clock remote monitoring. This one I will be skipping. I just would like to give you some hints, so I'm skipping. Now, when we say 24/7 monitoring, it's just including the alarm monitoring or remote resetting, notifications, logging of events or errors, and of course, user administration. User administration is informing you by an interface. You means both the site team, RDS center of Siemens, and the investor. Diagnostic support I've already covered. Software updates and vibration diagnostics also include all the susceptibilities of the breakdown will be assessed by the sensors, and we follow the vibration curves where the system is working. And these are the details that I'll be sharing it with you in detail in a minute. Around the globe, Siemens has more than 8,000 turbines running. It means that in the RDS centers, there is a know-how of 8,000 turbines. So there is a flow of all this data coming into the center. So this experience will just be accumulated in the center for that particular turbine. And when necessary, this know-how will be used if and when necessary. This is the screenshot. This is a snapshot of the RDS screens that we are using. Green, orange, yellow color codes are given. The reason for the color codes is out of 8,000 turbines, 24/7 monitoring, this is giving us the chance of easy detection for the experts. I mean, things are smoothly running, or there's an alert, a problem. So the degree of the problem is alerted by the color codes. The striking point is any warning that is received by the remote monitoring center by 85% can be resolved without any physical intervention or any site supervisor or the technician needing to arrive into the field. Every year we are approximately analyzing 400,000 cases, and we have an average response time about 10 minutes. You can see that 99.54% of all alarms are resolved. I mean, these are handled within the first hour. Now, for diagnostic support, we do use the SCADA system. It's a component of the RDS. Therefore, the data that is achieved from the turbine controls are flowing into the system, and it's accessible by the site teams. There is a field, there is an interface where the site teams can have access to its WPS. Here, it's possible to make tiering. Depending on the access authorization and the knowledge and the level of all the experts, there is an interference code that is referred, and everyone would be operating according to their authorities. Now, to give you an update, our remote monitoring center is based in Brande, Denmark, and for the manufacturing facilities, we have a plant there. It's just serving for the EMEA region, but still, all the turbines around the globe will be monitored in Grande, Denmark. Plus, Siemens is a world leader in offshore, you know, in market portion. So we have a very large offshore fleet that is running and installed. Merely speaking, for UK and around, we have about 4 gigawatts of installed capacity. Therefore, we have a dedicated IDS center. That's how it's being shared. There are 2 centers around the globe. Since it's 24/7, there is no hour distance, so it's no problem. About the software updates, you all are familiar with the software updates. It's available to the entire sector, so I don't want to get into the details of this aspect, but at least what I can say is vibration diagnostics is something that will just be in the position of detecting the previously occurred breakdowns. It's a mechanical breakdown detection system. There is a patching that is used to the vibration analysis. I think one of the most important advantages of the software updates is they're continuously feeding the vibration diagnostics. About that, I would like to highlight some points and give you some statistical data. When we are doing preventive maintenance, we are just making a preventive interference of a main component that needs to be replaced in 6 months, bringing down the minimum downtime, and it's possible to replace it with the minimum costs without causing any downtime or any loss of time for manufacturing. It's just the replacement time of the components that's taking. It's really a big advantage. I mean, it's an inevitable component of our turbines, and this is being extended to the entire sector. Now, let me just take a look at the hit rates. For the geared turbines and direct drive turbines, these are the locations of the sensors on critical points, particularly on the gearbox. You will not see anything here on the direct drive turbine. It's relatively empty nacelle because we have the permanent magnet where there is a revolution of that magnet. As a result, only in those spots you will find sensors. Since 1998, we have been providing the group monitoring services. We have acquired Bonus Company and started our position in the sector. And as an engineering success, I have to say, since 1998, under the umbrella of Bonus, and since 2004, under the umbrella of Siemens, we are providing remote monitoring. Therefore, the system mainly is relevant to the electronics and electrical systems. So this sector has been evolved, and we have launched a new RDS center in Hamburg, in a dedicated campus. So it's really a priority for us. Therefore, at this point of stance, I think the system has become quite a useful one. Now, more than 20,000 vibration analyses are being performed on the system per year. Also, we have a detection hit rate of 97% for gear tooth cracks, which means that we forecast a time span of 3 to 6 months, minimum 3 months up to 6 months. We have the chance of pre-detecting it, in advance, in all of the real cases by 97%. This is the 96% in the main bearing damages. Well, of course, I have to say that there is an internal communication system that is attached to it. If it's not available, of course, vibration diagnostics will not be available. The rate of operation of the system is 99.92%. This is a case example. When there is a bearing damage, it's a very small crack, but in 6 months it caused the turbine to become totally out of service. So being able to detect it so advanced, I mean, like in 6 months, it's like a very important benefit to adjust the crane operations. It's just a few hours of production loss, and it's possible to overcome this damage before it happens. There are different example cases. For the sake of time, I'm not going to get into that. Yes, that is the new RDS center. It's already finished, and for the last 1 month, it's operational. We have 130 experts for remote monitoring. I don't know if you know the session room of Istanbul Stock Exchange. It's similar to that. There are big screens where the entire turbines are being monitored. And now there is the office environment attached to it as well. Every remote monitoring officer will be in charge of some given sites, which would facilitate customer relations, field relations. It also makes the process to be run more effectively. It's also for the sake of communication. I mean, you will not be receiving any phone call from some unknown person sometime. That's the end of my presentation, and I think the questions will be received at the end. Thank you.
Zamanı da çok güzel.
Thank you for your time management as well. Well, as Ziya referred to in his presentation, of course, for a stable running of the wind turbines, there is a big know-how. There is a big effort that is to be spent. Both electronic and mechanical and construction aspects are important for this know-how. At the same time, the systems would require continuous monitoring because they're always in front of the eyes. Like a thermal generator of a diesel generator will not be visible, but the wind turbines are so visible that the people around will just be looking into that. Therefore, it's important that they keep running all the time. Now, Mr. Wolfgang Winkler will be speaking. He is from the DNVGL Energy, technical manager. He will be appearing to the floor and will be giving us information. For the last 18 years, Mr. Winkler has been in the wind industry, and I think will be making use of his experiences. Yes, sir.
Yeah, thanks a lot. Welcome to my presentation on operational wind farms. Yeah, more in detail, I talk actually about detailed monitoring to improve performance of the wind farms. Here an outline of my presentation. No, sorry. I don't know what's happening. Okay. Outline of my presentation. So short introduction of DNVGL. The general challenge of owners, operators of wind farms. What can be done with SCADA data analysis, so with the analysis of all the data, and more the benefit of detailed operational monitoring then. The short introduction, I have to do that because we merged about 1 year ago from Diagnostic Veritas and Germanische Lloyd, and still the name is a little bit unfamiliar to many. So we are #1 maritime company, technical advisor to oil and gas. I'm in the part of energy advisory where renewables is a major part of it, renewables and grid issues, and then we are also a certification body. For the energy, especially for renewables, a lot of branches, companies before merged to DNVGL Energy, specifically Gerrit Hassan on the wind energy side or on the renewable side, also with solar GL certification, and then KEMA, which is well known in the energy industry as well. For operational wind farms, maybe some statistics. So we did performance analysis of 50 gigawatts of wind farms worldwide. We provide short-term forecasting to 40 gigawatts in 16 countries. We do due diligence to a large proportion of the wind farms. We also have operate our own manufacturer-independent SCADA system, Windhelm. We did power curve measurements on 500 turbines, more than 500 turbines, and we inspect 700 turbines per year. So we have a little bit of experience on that. Coming to the actual topic, we have the owner-operator challenge. So what does anyone who owns or operates a wind farm wants? So first of all, of course, maximize energy production. That will be, he has to ensure the turbine efficiency and the turbine availability. The main things to investigate whether the turbine meets warranties and all these things, whether actual normal benchmarks are reached, and so on. Not only, of course, energy, but also revenue is an issue, which is not for sure always the same due to scheduling things of grid, due to price issues, volatile prices, and so on. So one has to assure also that the PPA is assured and things like that. Scheduling maintenance is another issue. Of course, also important for operation of wind farms is to minimize costs, or have the right amount of costs assured. So be sure that the predictive, preventive maintenance, which is actually paid in a contract, is also done. For example, that the prices are correct for any replacements, components, and so on. For all the third-party services. Is the right stuff doing it, and yeah, are the costs also competitive there? So a lot to do, and again, that was too quick. So maybe on availability, so one of the first points there, what can be expected is based on an analysis of 300 wind farms across Europe. Already done some years ago. But anyway, what you see, obviously, availability of turbines can't go beyond 100%. So that's the maximum value. You see then mean availability of 96% actually of wind farms, and that didn't change so much over the last years. And due to this irregular or not even distribution of wind availability, with some being very low. The average, so the P50 is slightly above 97%. That is what we see. That is a total system availability. And if you looked at the trend over time with a similar analysis, slightly modified, updated, you see that the green line here shows how many wind farms exceed this value. So this is a value which is exceeded by 50% of the wind farms, the green line, around about always, again, this 97%, depending on the year of operation. And slightly below, maybe in the first year, and then later years again. This might be also due to a smaller number of wind farms, which is then they are included in this chart here. But you see also that there are some wind farms, and usually that is continuous, that they're exceeding this range. So that they 25% maybe they are at the range of 98% availability and above. Also, of course, there are wind farms 25% which are here below the blue curve, so they don't match this criterion at all. So anyway, as we see that it's possible to reach 98% and generally also on a continuous basis. We think that should be the target. And from our experience, we see some correlation there, of course, to certain turbine manufacturers under certain conditions also. But moreover, our experience is very much that the operator of the wind farm has very much influence to that. So it's really also a target for the operator of the wind farm to reach that value. Of course, availability is one thing and tracked very often. But availability accounts maybe for 3%. As I said, we have an availability of 97%, so 3% of losses is covered by non-availability. But then you have to assure also for 97% of the remaining time of the remaining energy production that you operate the turbines efficiently. That was the second task. And on that, again, a similar graph operating efficiency. This on a smaller database of wind farms. But anyway, it shows a slightly similar shape. So it compares the normal power curve production with the normal power curve to the achieved one. And you see in that case it's possible to be better than the standard power curve, although it's rare. But you want to achieve actually 100% efficiency. That is what you expect, what your turbine is supposed to do. We see, however, that the mean of all wind farms is at the end 98%, and 50%, again, they reach 99% or higher. Again, that is also very much a question of detailed monitoring. So maybe put it in another way. With performance, if you had here just a example wind farm, whatever, which starts in the first year with the actual production being 100% above the budget value. So you usually don't worry. That's a usual behavior. But maybe you have even in the next year even further production due to windiness. In the third year, it looks maybe then entirely different, a low wind year, which can easily happen. Then you start wondering, what is the issue? What happened? What should I do about it? Is there a problem with the wind farm? And with the analysis, you might find out something that you could have produced during the years before, much more. So you can rectify it then at that time, but of course, there was an owner's loss before. So that should be the case. So what you should do actually, or what you would do for each operating time on different levels, you have the budget value, you have to make a comparison what was actually the wind resource during that period and what is the actual production compared to that. So that is here always showing the variance from budget. So maybe the wind resource in that example was first of all above the budget assumption. You even for the contractual availability, actually you have maybe been warranted with 97% or something, or let's say 95%, and you're close to 99% in that example. But there are other availability issues not covered from the warranty from the manufacturer. There you have then a loss compared to your budget assumption, also maybe on the power curve. And at the end, you have then this comparison of the actual how the actual compared to what could have been reached in that during that period. Yeah. So from our perspective, as I said, target should be 98% availability and 100% operational efficiency, but that is usually not reached, or often not reached. So here in a work-through example for a small portfolio of wind farm, for 3 wind farms here with around about 55 megawatt, production of 40 0.5 gigawatt hours here with a 30% capacity factor, which is maybe what you at least expect in Turkey, and 70 euro per megawatt hour income, which is maybe a little currently on the high side. Whatever. In this example, you get an annual input income of 10,200,000 euros, sorry, and so that means that 1% production loss means 100,000 euro. Therefore, it's really worth investigating time and effort to be sure that your turbines operate well. Yeah, what we would do for that is this SCADA data analysis, especially. So what you have to do is actually make best use of all information you have. So that is, first of all, the SCADA data from the turbines, from the substation, also fault logs per turbine and of the substation, the service records, whatever of the manufacturer or other contractors, and also monthly reports compiled by them. So if you looked at all these, you can have some analysis. Here's an example case study on availability. So you have to be sure that there are 1,000 reasons why the turbine is maybe not operating. Some are warranty issues, some are not. And here just an example. So here where you have the calculation. In this case, we had the calculation of a manufacturer in UK. It was, and he, at the end, the manufacturer calculated liquidated damages to be due in a year of 35,000 British pounds, which is of course money, but we did the analysis and came to much higher values. And after some negotiation about it, at the end, the accepted warranty claim from the manufacturer was 300,000 British pounds, which is, of course, remarkable. Operating efficiency, what you very often see in turbines, that they're not operating perfectly, so that they're accidentally derated, which you see more often than you would assume. You see component failures, so sensor failures, or especially wind vane misalignment is an open topic, and sometimes non-optimal controller settings. So, for example, that the pitch angle of the rotor blade is controlled in the wrong way, which leads then to lower rotations of the wind turbine and lower production efficiency. Yeah, here again then two examples on that. Wind vane alignment, again in a UK wind farm, where it continuously happened, then even after it has been fixed, that there are some wind turbines where the wind vane was not aligned perfectly, which led to the issue that the turbine was not facing the wind correctly, or some of the turbines, and that leads to certain losses. In this case, yeah, and it turned up again and again in this case, and it partly led to 150K on losses, and the remedy work, of course, was much less. On controller malfunction, here what I mentioned already, you can see this is always, again, you see here a power curve actually on the left, so 10-minute SCADA data of wind speed and energy production from the SCADA system, just as a relative measure. And you see there's some points where the yellow ones where the turbine is not operated well. You can see that from rotor speed and from pitch angle where the turbine behaves different than for other times. And this, if undetected, leads alone to losses per turbine of 30,000 euro. In this case, it was an example from France. That is one thing. So you can do these one-off diagnostics of wind farms, but you can also do this in detailed operating monitoring on a permanent basis. Depends what you need. So what you want then is, first of all these these things I discussed, these analysis done on a on a permanent basis. For that you need a good SCADA system, a good database management and efficient tools to work on that. Also, if you wanted to operate your wind farm, so you must understand what happened in the past to be able to optimize it for the future. But you of course need to have also active real-time control. You need of course also for that all measures on site become more important, like also health and safety issues and so on will become more important. For the detailed operating monitoring, you best have also good short-term forecasts, for example, to be able to provide efficient O&M at the site and so on. Sorry. Again, yeah. So maybe just as an example, what can be monitored additionally? We heard already about vibration, about the importance for to detect them for bearings and so on, to analyze that. We actually think that there's sometimes also an alternative way to do that monitoring, and that is by control of temperatures. So you have a lot of temperature sensors in your turbine. And from normal operation, you know what the turbine's temperature should be under certain load conditions, and that is, can you monitor then compare to the actual temperatures which you have. That is done here in that graph. You will have a certain threshold of temperatures, and here's a case study of a main bearing failure, which where you see that the turbine temperatures in the bearing increased considerably, and that led, and indeed after 11 months you saw that there was a bearing failure, and that took 7 weeks of replacement. So if you would have known in advance, as just shown already, it would have been much more beneficial for that replacement. Forecasting, it's actually clear short-term forecasting. It's shown here as an example. So you have the current production of the wind farm based on weather models, and the current production of the wind farm. You can forecast the future production, of course, with some margins of error, which are shown here. You might need that for grid management things if there are any issues. You might need it for energy trading, based depending on the question how the regulation is here and how it develops. And any way to be able to meet maybe PPA requirements. What you need also, especially if you had a portfolio of wind farms, maybe even from different manufacturers, you need to have, as operator, you have the challenge that you have data in many different formats, in different ways, different scalars. You need to put these together for any reporting as operator, and usually that takes all your time, so you won't have too much time for analyzing and optimizing. So you need to have some system where reporting is optimized, where it works well together with the different systems, so that you have can you spend your time with analysis and optimizing of performance. So our solution for that would be our the Windham SCADA database system. Maybe you know that DNVGL provides a lot of different services, and these are So we would also provide a lot of these services as described, and can be combined in full asset management, as we do now start to do. So one thing is, of course, one major thing is, of course, monitoring, the management of the plant, all technical issues with contractors and so on, also commercial management and health and safety coordination to reach smarter operations. Maybe then a summary, just the conclusions. What you need, first of all, as owner, as operator of a wind farm, you need to have good data quality, visibility of all information. You need to have this combined, which is a task in itself. Based on that, project availability, 97% is widely reached, but with good monitoring, we assume that you can reach 98% and higher. And for operating efficiency also, the 100% benchmark figure is often not reached, but it is almost possible, at least. Yeah, for that, you need to have good monitoring techniques and analytical tools. Inspection, maintenance is, of course, required, and informed through condition monitoring potentially. And yeah, of course, also very important are the different contractors, and you need to work well together with them, but also proactive. Try still, of course, always to remain in good relationship with them, especially the turbine manufacturer. Okay, thanks a lot for your attention.
Availability is one of the most critical issue in your presentation, which we all have to take care. Yeah, thank you. By Marios.
Mr. Marios Papagorgio from Fitchner, senior mechanical engineer, has a vast field experience, I have to say, and he has been in charge of processing the field information on office. It's always an advantage to do that, and he's currently working in Fitchner. Thank you.
Thank you very much for the introduction. It's Papageorgiou, to be precise, but never mind. I listen to Marios all the time. I've been in Turkey for 3 years, and I'm honored to be in the Fitchner family for the last 1 year. I'm going to present some issues of the construction phase of a wind farm, some of the most common problems, and how an owner's engineer can help to reduce these problems. First, I will introduce Fitchner from worldwide size to here in Turkey. Then we're going to mention the life of a wind power plant project, and then explain why technical consultancy is necessary for the wind farm construction. We will demonstrate some of the most common problems during the construction phase and how owner's engineer can help to mitigate the risk created. Fitchner is Germany's largest independent engineering and consulting company, founded in 1922 by the Fitchner family, to which it still remains. With a total of 1,800 staff globally and presence in more than 50 countries, it's a leading expert in the sector. It currently has 5 established wind teams in 4 countries, UK, Germany, Italy, and Turkey, providing services all around the world. Fitchner has been working in Turkey for more than 40 years and has established a branch in Istanbul in 2008. Since then, it has been active in all energy sectors, combining an experienced pool of engineers around the world with local experts in order to provide the highest possible quality. Fichner Wind team in Turkey has worked in almost 100 projects locally, a total of around 4 gigawatt in all parts of the project's life and various services. More than half of this number concerns energy yield assessments. It has also supported projects in Italy and Romania. Obviously, not all projects I mentioned have been realized yet. Services provided include owner's engineering, lender's engineering, technical due diligence, inspections, and energy yield assessment using both known technologies of WASP and CFD. Specifically, owner's engineering is performed in a way that adds value to the whole project's life from initial idea to the advanced operational state. The project's life starts years before construction, and it's a very time and resources consuming process. The better each stage is prepared and implemented, the more cost efficient and productive a project will be. More specifically, for the construction phase that we are examining today, it is the hardcore part of the process. Transportation, civil, mechanical, and electrical works, as well as turbine erection and commissioning take place during this time. All need to be coordinated well and realized in the most effective way, as obviously almost none of them can be repeated without extreme cost. How does technical advisor support the construction as owner's engineer? He does the hard work of optimizing, controlling, recording, and verifying the operations during construction. A lot of people know their job very well, and they believe that they don't need anybody else to tell them how to do their business, until something will go wrong. In the time of dispute, lenders, insurers, and subcontractors will trust a documented, experienced engineer. Even if everything will be completed perfectly, the documentation and experience shared will be added value to the rest of the project's life. What are the classic problems during the wind farm construction? First one is time schedule. It's a nightmare. It's hard to construct, difficult to follow, and impossible to achieve. Secondly, quality. Although everybody knows that all the major suppliers have a very high level of quality and R&D, in the construction phase, there are more people working than just the turbine suppliers. And as years pass, more and more locals will be included. Quality issues occur in the plant's balance as well as the turbines themselves. Another issue is turbine and implementation, the design and implementation. Did you get what you ordered? Is it in the proper condition? Another issue is communication and interface. Where does one subcontractor's work end and the other start? Last but not least, accidents. Who pays for them? Could they have been avoided? Starting by the time schedule, what creates the problem is many factors, but mainly weather conditions, because we have started the construction in the wrong season of the year, or because of an weather incidents that change the route of operations. It can be faulty planning, because erection cannot start, for example, if the parts are not there. Commissioning cannot be completed if there is no grid connection. Last, I will mention licensing and authorities, because one can assume a typical time frame for a license to be issued, but cannot predict any delay due to inexperience, dispute, or even holiday. The result is delays from some weeks to years with amazing costs in storing, maintaining, or of course production loss. Second issue I would like to mention is quality. As I mentioned, turbine suppliers know their job very well, but they're not the only ones on site. Even if they take an EPC turnkey project, they will use subcontractors. And then cost will have to be dropped, and then quality issue arises. Common problems: roads, crane pads, not meeting the standards, assisting buildings with problematic construction, water and cable trenches might hide surprises, and turbine assembly, yes, they also might perform poor. As a result, excuse me, possibility of accidents, time delays, poor turbine performance, often outages in the operational period. I will show some photos of quality issues. This is a cable water drainage which is blocked by the first rain. This is a cable trench turning into a water trench. This is another cable trench with hidden surprises. This is a road issue that might have a problem in the transportation. And this is during erection. As you can see, the blade is almost touched by the crane. Design and implementation. Bringing what is planned on paper regarding material and procedures to an actual project is always a challenge. Sometimes the factory might send something similar that is not proper for the project, or even if it is proper, it is not the one agreed according to the contract. Second, transportation process can always add some souvenirs to the components. Storage might be inadequate. Many times heating, rotating, lubricating is needed. Last, a technician without the correct tool but with a tight schedule can prove to be very creative on site, but at the cost of the components and future use of the turbines. Result is at minimum an overcharged item, but most usually underperforming component, or even worse, an accident. Some examples of design and implementation issues. This is a tip of a blade where there should be a drainage hole. As you can see, it is closed and painted very nicely. This is a road souvenir, transportation probably, a road that has been hit. This is damaged gear inside the nacelle and corrosion on the main shaft. Communication and interface. The mix of technicians and specialists from around the world, as well as a mix of subcontractors working all together with tight schedule, can cause misunderstandings and dispute on the site at the worst possible moment. In a critical point, no one knows who should do what in the interface of two processes. Cable is here, switchgear is here. Who is going to connect them? Who is going to buy the fitting? And who will be responsible in front of warranty? As a result, arguments, delays, and negative communication. Last, I will mention accidents. The worst case scenario in an accident is a human getting hurt in any way. Other than this, it affects equipment. For both personnel and equipment, there are always ways to keep record of the rules followed or even to create new rules on the way. Health and safety is often neglected in sites treated as a delay factor, while in reality, health and safety procedures should be part of the plan. There is no delay when there is a plan followed. As a result, health and safety is often underestimated, so unexpected incidents cause more delays to the project. For examples of accidents, I don't want to show any scary photos, but some examples of material being hurt or human almost getting hurt. A tower rolling down the hill is something that we have seen quite a few times. In this specific case, the support of the tower had a crack, and the support of the support with the first rain became muddy. In this case, our friend is doing a lot of things wrong, inspecting a ship, no shoes, no harness, no helmet. In this case, both human and tower might get hurt very soon. As you see, there is no support properly adjusted to the tower. In this case, one of the blades missed its protection, resulting to a nice crack. How does owner's engineer service support and mitigate problems during construction phase? First of all, technical advisor works for the project, not only for the owner. Everybody wants the project to be completed successfully, everyone for their own reason. Owner wants to have a productive plan for years at the lowest possible cost. The supplier wants to finish, deliver a proper project, and move on to the next one. Lender, in is interested in his money. He wants to be sure that he will take his money back in time. And all other subcontractors need the reference in order to get more work. A consultant may help by planning a feasible time schedule and then monitoring. This is a dynamic process. Owner's engineer will make sure no unnecessary delays are there. He will document and provide valid arguments in the negotiation table. He will provide consultancy to any possible problem by bringing to the table experts from all around the world with the proper experience to address each specific event. He can remain on site at all times and attend all meetings and procedures during construction. He will ensure that this way proper quality. He can monitor or prepare reports and records for all activities and events for later reference. And last, he will support the owner's staff and project manager by sharing experience and methodology, something that will improve the owner's experience level. This is a typical diagram of interface with the owner during construction period. You can see that the engineer supports the owner but does not take over the project. Owner has full control and makes the calls, but the engineer helps by transferring the owner's will to real action on the project. This is a diagram of our internal interface for such a project. It is obvious that the simple box that you just saw in the previous slide includes a very large depth that owners practically cannot support. For closing, a financial slide. This is the simplified charts regarding the cost of a wind farm per megawatt. And you can already see that at about only 1% of the investment cost is the cost for the consultancy. Putting this in real numbers, it is more than clear that the benefits from using an independent consultant for the project construction phase has a lot to offer to the overall value of the project. Thank you very much for your patience.
Thank you for the nice photos also. Quality and health and safety, they are just linked to each other a lot. I'll just speak in Turkish for the rest. İş güvenliği.
Of course, about labor safety security, which is really a popular issue in Turkey because we have the new law that is in force, and because of the unfortunately bad experiences, it's just a matter of priority. But it's not a standalone matter because it should be discussed with the environmental impacts and quality content. And one of the things that might be missing in Turkey is the perceptions are evolving as the international investors are getting to work more in Turkey. The local investors are getting more aware of health and safety, and I believe that more significant steps will be taken on that in the future. Last speaker of the session will be Mrs. Eva Maria Schmidt. She has a very strong academic career, and she is working as the head of group site assessment with Windtest company. You're invited to the floor, madam.
So, ladies and gentlemen, first of all, I wanted to thank the TWEC committee for giving me the possibility to be a speaker today. My name is Eva Maria Schmidt. I am head of the group Energy Assessment, and I'm working for Windtest for 6 years now. So the contents of the presentations, 4 main items. Unfortunately, the second one, energy assessment, is not a main focus of this session, but I hope it's interesting for you nevertheless. So the first item is a presentation of Windtest Grevenbroich. Then the chapter energy assessment, technical due diligence, and some of our references. So as you can see on the photo, we are 50 colleagues, mainly engineers and natural scientists, IT and administrational specialized staff. Windtest was founded in 1996, and we are accredited. We are doing prototype measurements and expert assessments. And we do have 2 test sites for our prototyping measurements. One is in Grevenbroich, where our office is located, and the second one is in Lelystad, the Netherlands. 2014 is a special year for us because we founded a new office in the US state of Iowa. And we are a MESNET member. MESNET is a network of measuring institutes in the wind energy industry who take care of working out guidelines in order to guarantee a high quality for measurements. Our managing director, she's also head of, she's also the chairwoman of the MESNET committee. So what are we doing? Historically, the first division of Windtest was the prototyping. So we're working for manufacturers and measuring power curve, the loads on wind turbines, and sound emissions. And we're also measuring the grid characteristics of turbines. For that, we use the container that you can see on the photo. It's a low voltage ride-through container who simulates a fault and is testing the reaction of the wind turbine to know if it is reacting like it is supposed to, by increasing reactive current to stabilize the grid. So we have 2 own containers to do this fault ride-through experiments. Where are we working? We do have global projects. We're doing, for example, vibration analysis in the US or the measurement of sound emissions. We're doing energy assessment in Chile and Uruguay, and power curve measurements in India. And the focus still is in Europe. So most of our projects are in Europe. In Turkey, we have 5 years of experience in energy assessment. We did assessment for major wind farms of 50 to 70 megawatt installed capacity in the province of Izmir. Some clients are, for example, Lodos or Ezinti. So the second chapter of my presentation is energy assessment. Regarding the upcoming tenders, I thought maybe that would be interesting for you. Often we have complex terrain in Turkey. On this slide you see the green represents sea level and brown is 900 meters above sea level. So we have a very complex site. In order to do energy calculations or the calculations for wind conditions, we use CFD tools, and we have used them since 2008. We are regularly supervising students who do their final thesis final works in the field of CFD, for example, comparison of different CFD codes or different forest models in order to get more experienced. And what we do is to hire these students so we can use the know-how for our energy assessment team. General requirements for high-quality energy assessments are the wind data. So the MetMast has to be constructed or installed according to the IEC 61412-1 guideline. In order to guarantee a high-quality measurement, we collaborate with the Turkish company Usense. They are doing the installation, maintenance of the MetMast. What we can provide is the calibration of the complete measurement chain. So not only of the anemometer in the wind tunnel, but also of all the components that are connected, like cables and logger. And we're doing acceptance checks or inspections of the MetMasts. If it takes too long to obtain a building permit for the MetMast, you also have the possibility to measure with remote sensing devices. There are restrictions according to the terrain that have to be taken into account. But in general, I will explain how the system works. Remote sensing devices like LiDAR systems, which works with laser pulses, works in a contactless way, so you don't have to put a sensor on 100 meters height above ground level to know the wind speeds there. It measures the wind conditions from the ground. And it sends out laser pulses, which are reflected or backscattered by dust particles in the atmosphere, and are conducted to the detection unit, which is on the ground. And the basic assumption for the use of this devices is that the speed and the direction of the dust particle is the same as the wind speed and the wind direction. According to the new guidelines, so first of all, the power curve guideline, the IEC 61412-1, the draft, which is not valid now, but and the technical guideline 6 that is relevant for energy assessment in Germany. You cannot use a LiDAR or SODAR or any remote sensing device without validation against the industry standard of MetMasts. So to ensure the comparability, you have to do a parallel measurement of the two devices, so the MetMast and the remote sensing device, and do correlation analysis. We can do this on our test site. We have a validation station where we have a MetMast, which you can see on the right side of the photo. What you also can see is a lignite power plant in the background. So the town of Grevenbroich is not the capital of energy because of its wind energy, but because of the lignite power plants. So the MetMast is on the right side, and on the left side you can see the container which contains the lidar systems and a sonar system which is placed next to the container. So this is where the validation is executed. So now we're coming to the next point, which is more related to this session. It is about technical due diligence. What is technical due diligence? It assesses the technical status and quality of a wind farm project, and it is done based on paperwork. So we only use contracts, technical specifications, assessments for the assessment. It is done for investors, developers who lack the know-how in a specific field of the whole planning, operational development of a wind farm project. And since there is no guideline available for doing technical due diligence, we developed a checklist in order to facilitate the process. It compromises all of the single fields within the planning or operational phase. So, for example, the assessment of the road access, building permit, site assessment, micrositing the wind turbine, the assessment of the technical inspections, etc. So this is how it looks like. We have a traffic light for every field of assessment. So in this example, we have a sorry. So now we are back in again. For every field of assessment, there is a traffic light which changes its color due to the results of the assessment. So for periodic tests, technical inspection, we have, for example, the knockout criteria, rotor locking mechanism is working or not, or the mechanical brake requirement is fulfilled or not. And if all requirements are fulfilled, the traffic light turns green and you can proceed to the next field of assessment. So we're coming to the end of the presentation. I wanted to show you some references. As I told you, we're working in the prototyping division for manufacturers. So our clients are, for example, Nordex, Gamesa, Enercon, and in the field of energy assessment, technical inspection, we are working for investors and developers like Gotha or RWE, UV, and on the Turkish market for Lodos Electric. So the conclusion of the presentation, Windtest is an accredited service provider for prototyping measurements and expert assessments. We are working in the field of energy assessment and provide CFD calculations, validation of remote sensing device, or the calibration of the complete measurement chain of MATMAST. We the MATMAST are installed and maintained by our Turkish partner USense, and we developed a checklist for technical due diligence. So thank you for your attention.
Thank you. Rüzgar enerji santralleri.
Now, we have come to the end of the panel that was about construction processes and management of wind power plants. We've tried to provide you a different perspective. I might assume that you would have questions to the speakers. We can get the questions, if any, now. I was proven wrong, I think, huh? We don't have any question. Then thank you very much for your attention, for coming here, for attending the session. Good afternoon.